So, did you all make it here? I see some losses halfway, but here we come now to one experience. And actually, this presentation now is given by Andres Valinskis from Finnish Meteorological Institute, just arrived from Finland. We're actually our old team member who now stayed in Finland for a year to learn the best from Finnish experience. But the topic he will present is actually the newest results. We have from ST1 so long work of 1.5 years. Some of it was presented already in Mallorca. Some of you were there at Forest Conference, but we have a lot of new analysis and results, both about the camera system and latitude determination. So, Andres, the floor is yours.
Thanks. All right. It's nice to be here. It's nice to visit Observatory again. So I will talk about two topics which are somewhat related, but still there are separate subsystems on a CubeSat. One is camera, and that's not my native topic, so I'm sorry if I can't answer some questions. And the other one is attitude determination and qualization of that. And also this will include the newest developments of camera system in the ESEO project, which is European Student Earth Orbiter. But now a bit with an overview. So who of you doesn't know what's electric solar wind sail? Okay, everybody knows. Nevertheless, I'll go through a few points, a few main points about this propellantless propulsion system, which is based on charged long thin tethers that interact with charged tethers in the solar wind. And this principle, or this technology, is invented by Pekka Jankkinen, who will give a talk tomorrow about the space exploration using the e-sail. So if it proves to work as we expected, then it would be a record fast transportation in the solar system, and it would also enable new missions that nobody has really thought of, but it has to be tested. And here comes the ST1 satellite, which carries the first in-orbit experiment of the electric solar wind sail. When I said long, thin tethers, so tethers are thinner than a hair, and the length might be, let's say, 10 kilometers, but we have to start with small things. So in ST1 we have a 10-meter long tether, and we are in a very popular CubeSat orbit in a very popular orbit for CubeSats, in a low Earth orbit, where instead of solar wind we have an atmospheric plasma. But more about these tether experiment, let's say updates, will be given by Martin Norman tomorrow, and I won't talk about it today, and that's intentional. So then a small overview about subsystems. First of all, the ones I will talk with. Camera's main purpose is to image the end mass, which is a small piece of aluminium at the end of the tether, but we have also used it for many other things. Then attitude determination system, which would provide measurements of the e-cell force, and also would provide input to the attitude control system. Then there's an attitude control system, which you will find more about it in hopefully some 20 minutes when Henrik will talk. And then there's electrical power system, command and data handling system, communication system, and structure. And about structure, Paul will talk tomorrow, but not exactly about ST1 structure. But now, so I'll start the most the difficult part about camera. So here's the camera design and also an image of it, and also how it's integrated in the system. So the whole so this is a CubeSat. It's 10 by 10 by 10 centimeter satellite, and the camera, you might guess already approximately the size. It's 4 by 2 by 4 centimeters, and it has 640 times 480 pixel image sensor, and it weighs only 30 grams. And so it's an independent module, meaning that it has its own microcontroller and storage, instead of just being a peripheral of an onboard computer. And it's like similar as with other subsystems. It's connected to the same bus, and it has its own MCU. It has 120 megahertz Cortex M3, which is actually the most powerful processor on SQ1 due to the tasks of image processing. The system has also voltage regulators and current sense amplifiers, and those are separate for the image sensor and the MCU. And so, yeah, that's for testing and debugging the system. So the system is also FRAM and temperature sensors, also for both MCU and behind the image sensor. Regarding optics, it has a 4.4 millimeter telcentric lens, and regarding filters, it has 25% neutral density filter and 700 nanometer infrared cutoff filter. And then the systems like sensor, lenses, and electronics, they are detachable from each other, so to provide sort of portability to other systems, and it would be easy to adjust to other systems. So the system was launched with the basic, as with most of the ST1 subsystems, with the basic firmware, let's say with the minimum firmware to lower the risk of sort of having too many functions, something going wrong. But since there were on subsystems there are bootloaders, so we were able to update all systems, and that also includes camera, which has had 2 firmware upgrades. One was to provide sort of the functionality that we wanted for the camera to have. That would include things like histogram-based evolution on board the satellite, so we would be able to analyze when we have the Earth in the image, or when we have dark sky or space, and when we have sun. And so at the beginning of the mission, we had images like this, most of the images like that, because they were. And then this is also due to the fact that at the first phases of the mission, attitude control didn't work as we would like it to work, but Henrik will talk about it. So basically, satellite was tumbling randomly, or in a way that we didn't control it, and so this functionality to analyze histogram on board gave us a chance to take images like this, which are nadir pointing and which are arm cloudy. And then came the next software update, and that was to decrease power consumption from 120 to 75 milliwatts. And also we have sort of analyzed since there are temperature sensors, you can analyze the temperature next to the camera, and despite the fact that the camera is basically at the side of the satellite and without really much covers, it doesn't have a shutter, for example. The temperatures that we see are between 5 and 25 degrees, which are, let's say, the range is better than we expected, and then this range is sort of comfortable for the camera. Then the next thing is degradation, and basically how the white balance changes. And here you can, in this image, you can see this is the first image that was taken in May 2013. And in this image, all the gains for all the colors are set to 1. But then, over time, the images got yellower, and that was due to the fact that if we relatively plot the gains, then the blue and the green one decreases, and we keep the red one constant. And so the gain correction is also done on board instead of doing it after taking images and downloading them. Then, if we correct gains, we can get an image like this, which is, where you can see that clouds are white, so it's in the balance. The white balance is correct. And so this is, of course, it increases noise, and one cannot do it forever, but still, if the trend keeps that way, then we can do it still for a few years, and even then, one would be able to take grayscale images. Then also analysis of dark frames, which is basically we take an image of nothing being in an image, and then we see like light pixels or hot pixels, and these are basically burned by radiation. And here we can see the relation between time and number of those pixels. And this isn't a complete analysis; it's still ongoing. But so basically, these numbers mean approximately 0.25% of permanently damaged pixels. But we haven't seen any sort of. You don't see yet that image quality gets lower because of radiation. Then, in meantime, while fixing many problems with attitude determination and control, or solving problems, let's say, more than 230 images were taken, and here in this figure you can see more than 100 of them, and this clearly statistically shows where the most images come from. They mostly we have imaged Africa because of two reasons: because of cloud cover and because of the satellite's orientation with respect to the magnetic field. And when the attitude control started to work, we have acquired also images of the other parts of the world, including Estonia and Latvia here, and which was the secondary mission objective of the project, to acquire such images. So, sort of concluding about ST1 camera, the camera has met all the challenges, and so it has worked much better than we expected, and we have taken much more images than we expected. Like, a camera engineer had an image counting system from 0 to 99, and that failed quite quickly, that system. And then I'll talk a bit about European Student Earth Orbiter, which is a student-built satellite, and payloads are built by European universities. And the bus is built by Almaspace. It's a very good logo for a black background. And in this project, Estonian universities, led by Tartu Observatory, are responsible for making a optical payload. And the optical payload is mostly is meant for PR reasons, to take nice images of the Earth. Nevertheless, we are taking sort of redundant approach for this. So there are two cameras. One of those cameras is the same camera that we have on ST1, with just small changes of the mechanical interface to comply with the big set, the overall mission, the overall requirements, and also we fulfill the requirement to have use the CAN bus. So both carbon fiber and aluminium structures are used in making the frame for the camera. The camera has baffles to sort of deal with unwanted light, incoming light. As I said, CAN interface, and so also in addition to that, there's the onboard computer for the whole satellite. Also for these two cameras, there's an onboard computer to log temperatures, current consumption, and voltages on SD cards, as well as a functionality to transfer files. So, as I said, all the primary payload, we call it primary payload, because it has a space heritage. So we are quite sure that it would work, and it has Canon SPA interfaces, and taking into account the predicted orbit of 520 kilometers, there would be, so resolution would be 630 meters per pixel. And then secondary payload, much larger camera with much bigger optics, and with this, so and then 5 megapixel with 5 megapixel sensor. We predict that it would be possible to get 23 meters per pixel, and additional SD RAM and mass storage. Then so this is all about camera. So by now we have covered ST1 camera, ESEO camera developments, and now I will talk about attitude determination system. And first, a bit of an overview of what the system consists of and what it is supposed to do. So it's supposed to determine the accuracy, determine the attitude with an accuracy better than 2 degrees. It uses magnetometers, sun sensors, and gyroscopic sensors to get attitude measurements. It uses Kalman filter to sort of merge all these measurements together with respective models to determine the attitude. Sensors were calibrated in the laboratory, but we recalibrated them in orbit. We recalibrated and tuned them in orbit by either comparing their measurements if they basically if you have if you know that the angular rate is that and that, and so we should see that the magnetic field changes with a similar, at least with a similar rate. So then the next method was to compare these measurements with models. Geomagnetic model, we use IGRF, and sun model, and then also angular velocity measurements could be compared with Kalman filters output to have sort of feeling if things are working, if all the things are working together. And we validated the system by comparing the attitude from the system with the attitude determined from images. And this is where the camera played a significant role that we didn't actually plan. So here's a small flowchart of ADCS, starting from measurements, ending with processing on board and comparing post-processing phase. So we have 2 magnetometers, 4 gyroscopic sensors, and 6 sun sensors. One sun sensor per side. And then for calibration or for measurement correction, we have 2 temperature sensors. And with all these sensor measurements are processed together at the end to get a temperature, magnetic field, angular velocity, sun direction, and we call it a pre-processing or low-level filtering or processing. And then when we have these processed results, we can input them to Kalman filter, but Kalman filter also needs reference. So for that we have a sun model and also magnetic field model. And magnetic field model requires Earth's rotation to be model, and it requires the satellite position. And in addition, we need to have a guess how good our. This is sort of, we know that this should be 20 milliseconds because we want to know exact time. When are we going to start to do the attitude control? And that's needed to extrapolate attitude for exactly this moment. If one does low spin rate maneuvers like up to, let's say, 5 degrees per second, this wouldn't be needed. But since we need to do maneuvers up to 1 revolution per second or maybe even more, then this is critical, because if one estimates attitude here and then it starts to control it after whatever, let's say 100 milliseconds, then the attitude is already quite a lot off. Anyway, and while attitude is controlled, on attitude determination side, we are running models, sun and geomagnetic models, and Earth's rotation and orbit propagation. Then we do attitude determination, and then the attitude is the main input to the attitude controller. And then we wait that the attitude controller will end. And as I said before, during this determination, we do it for the moment. So we can say already before determination, we extrapolate all our measurement vectors to the middle of attitude control. So then about this small visualization how we measure the attitude from images. So this is a nice image to post on Facebook with colors. But to estimate the attitude from images, we don't need colors, because what we are looking for is points on images which are easy to distinguish. And so when we find these points in images that are easy to distinguish, we can find the same points on a 3D map or a globe or whatever you call it nowadays when they are in Google Earth or Bing. And then these two sets of points, one's from images, 2-dimensional coordinates, and one's from globe, where we have 3-dimensional coordinates, is an input to the attitude estimator, that to determination algorithm, which outputs, from which we get attitude, and we usually take many points, let's say 15, 20, then so more statistical methods can be applied to do it, to get higher precision. And of course there's, since the points are selected by somebody, then there's also some human error factor. Then we did another, so we wanted to find out how good are our measurements with the attitude determination system. And what we have is, we have two measurements from two independent sources. And we can calculate differences between those, but the difference itself doesn't necessarily mean everything. So we want to know uncertainties of both systems. So here's the uncertainty budget for the attitude determination system, and the components that we pinpointed as the major contributors are, first of all, coming from previous research that we run simulations with in which inputs were the lab measurements of sensors, where we fairly well estimated their uncertainties. That's an input simulation. So from that, we found out that the uncertainty estimation by standard deviation per modal one is 0.6 degrees. Then we also take Earth precession into account, 0.15 degrees, Earth rotation, 0.1 degrees, and orbit propagation, sun direction model, and geomagnetic model. And with these all, I didn't write down references because it's quite a long list, but if you want, I can give you all the references to these. So it all, at the end, it all adds up to expanded uncertainty to 1.26 degrees. This is from onboard attitude determination system. Then we also need uncertainty of the image-based attitude determination, and here we pinpointed these contributors like point selection uncertainty, then so yeah, basically point selection uncertainty, that's what is the average difference between vectors selected on both coordinate systems, and then yeah, this gives it. So this gives this so-called human error. Then time uncertainty, because the ADCS measurements are not perfectly synchronized with the camera, and there the time was varied in order to those measurements to find the best fit, and that step that was used to vary the time introduces 0.21 degrees error. Then we have smaller contributors at resolution as length and as length distortion. So it all adds up to 0.86 degrees. From that we can get, adding both uncertainty budgets together, we can get 1.52 degrees. And here in this table, we had 15 samples where we took attitude determination measurements together with images, and from these samples, basically the biggest difference between both attitudes is 1.43. I guess 1.43, and which is within our uncertainty budget, giving us a hope that the uncertainty budget is correct, and also that let's say that the uncertainty budget is aligned with mission requirements, and also that we haven't seen bigger differences than is predicted by the uncertainty budget. And to conclude, since I have developed camera, I can say it's one of the best cameras in within CubeSats. It fulfills all the mission requirements, and its heritage is to develop the camera. Its heritage is used to develop a camera for SAO mission, and this mission is scheduled to be ready on the first quarter of 2015. And regarding attitude determination system, we have that calibration, characterization, and validation. And here we can add that implementing in-orbit calibration methods might be a very nice way how to improve ADCS measurements. At least that is our experience. So the uncertainty budget fulfills mission requirements, and results of comparison are within the uncertainty budget. And this lessons learned, so and the heritage of attitude determination system will be used or is used for future missions or future ESAL test missions. Okay, thanks, and sorry if I'm too long.
Thank you, Andres. Do you have any questions to Andres?
Yeah.
I'm skeptical about the number that you had for the error in the geomagnetic field, uncertainty of the geomagnetic field direction. I think you had 1/1000th of a degree in your slides. Maybe that's a typographic error. Maybe.
So you mean?
Yeah, that one. Yeah.
Yeah. I mean, I haven't done an analysis myself, and this is the best. I just found one reference that gave that number. But to be honest, I have to say that in that analysis, they predicted this error so the model is now from 2011 to 2015, IGRF 11, and they predicted that error at the beginning of EPO, or when they made the model. So I didn't find any analysis that has taken measurements and compared it with the IGRF 11. I didn't find any.
But I mean, if it's only IGRF model, then one has to add also the contribution of the magnetospheric current systems, which add maybe tens of nanoteslas to the field. So that would multiply that at least by 10 or maybe 30. This uncertainty. So this number might actually be even correct for the IGRF itself, but it's not the same as the total magnetic field that you have in orbit. Because you also have the contribution from magnetospheric current systems, which depend on space weather and which are therefore not possible to predict.
Okay. So then probably I got their sort of message from their article a bit incorrectly.
Yeah, but anyway, it doesn't really affect the final result very much. So
thanks.
Any more questions?
Was there any requirements for altitude determination during eclipse time? Have you done any analysis on the performance during the eclipse?
Only simulation based, and so of course the error increases quite a lot. I mean, I would say tenfold, but we don't really need it during the eclipse, and I'm not even sure if we have tried to do it in eclipse. So I mean, there's no requirement to determine that in eclipse.
Yes, I have a
Thank
question.
Yeah, please.
I have a question about selecting points in the images, and that's done by human.
Yeah, that's like zooming in
And
and trying to understand which point represents. So in these 3D coordinates, you can get very nice. You can zoom in like a lot, but then to understand which pixel on the ST1 image represents that point, that's a bit.
I've heard of this method, but I think there's calculating that do this manually based on the
Automatic.
automatically based on the
Yep, we looked into we tried to look into that, but so first of all, it might. I mean, I know it's possible. I have done similar things myself, but it's always a good playground where you have it. But then to put it together, okay, we know everything about our images, but where to get the 3D coordinates of 3D sort of image of the whole. I mean, where to get the globe. so that you could write an application programming interface to do it. That would be, I don't know, quite difficult. So I think it's easier. It was easier to do it by hand, and so this point selection uncertainty wasn't that good.
Maybe we don't take more questions because Andres will be with us all evening. And after lunch, which is already served and it's cooling down already for 10 minutes. Actually, I told them that we will be late by half an hour. Don't worry. So maybe after dinner, we will squeeze out from Andres everything you want to know. But thank you, Andres, very much for And now follows presentation by Henrik. And as you understand, attitude determination is not a thing by itself, but it's mainly needed for attitude control. And results of the control, some of you know that we had quite a lot of problems with that over this year, with some really big problems. You have seen hopeless at some point. But then Henrik, together with Johan, started to work on it, and let's see what they figured out.
Yes. Okay, it's working. Are you getting fine? I think so. So, my name is Henrik Kefais, and I'm from Tartu University. I'm an undergraduate student of physics, and I'm on the final year. So, first off, I start talking about what is attitude control and what are the mission objectives for attitude control for us. And first off, I will talk what makes our attitude control system special, and that is that we want to spin the satellite up to 360 degrees per second. So as you can imagine, it's very fast. It's rotating 1 revolution per second, but we need to do it because we want to deploy the tether that Danish was talking about in the last presentation, using the centrifugal force. And because the tether tension has to be within certain limits, then 360 degrees per second is optimal for that. We did achieve that. We can say that we achieved that goal also. So that is one of the high points for attitude control for us. But now I'll talk about the other objectives a bit more. So our main design goals was to keep the power and mass requirements at a minimum. And so we only have one unit CubeSat, so that means we don't have much mass to go around, and we don't produce much power. So for attitude control, we also need to align the spin axis with Earth's polar axis. It might not be easy to understand that, so I'll show it a bit later in an animation, and I hope you can understand from that more. And one more important thing is to minimize the forces acting on the experiment tether, and that can be done by reducing nutation to the minimum, and that is done by the spin controller, basically using attitude and other attitude determination inputs as an input to the controller. So for the next slide, I will talk a bit more about what our attitude control design is. So we only have 3 electromagnetic coils, which are not the strongest. So the power that our attitude control has is not very big, and we don't have anything like reaction wheels or something like that. We only have 1 electromagnetic coil aligned with each satellite axis. So we also have controllers, so I'll talk a bit more about them. Basically, spin controller is the main one we are using, and it is based on, it uses as an input the attitude and magnetic field and also angular velocity. And basically we toggle our coils on and off according to what the spin controller tells us, and that is basically the fancy graph that Andres showed you before, the one with the timings. And we also have a simple controller for T-tumbling, but it should be noted that it's almost impossible to use a simple controller for key tumbling at angular velocities like 360 degrees per second. And it is not working for us, a simpler controller at higher angular velocities. And we also made a pointing controller, but unfortunately it is not working because, as Mark already said in the introduction, it wasn't all sunshine and rainbows with attitude control, and this problem is basically unfixable currently for SB1. But we will still try something maybe when we have free reign over attitude control again soon, when the experiment maybe concludes. And one of the design goals or requirements was to use coils as often as possible, because then we don't waste power while operating AVSS, CDHS, and different subsystems which take a lot of power, and we are rather power limited. And basically that is done using again this timing scheme that while we are using the coils, we are actively calculating the attitude and doing the control at the same time, basically. So a quick picture about how the coils are mounted on the side panels. One of them is turned upside down, but you can see this is basically the coolest picture we could find about of them. And yeah, few words also about the strength of them. The magnetic moment they can produce is 0.09 amperes per amperes time meter squared. And we learned to make them, because these coils are made by the SQ team. We learned to make them from Aalborg University, so big props to them for letting us learn how to make them. And then we created our own coil maker, and now we have the ability to make those coils ourselves. So to talk about the most interesting part, so what went wrong for us, or what the other attitude control systems should do differently, or expect those problems and try to prepare themselves for them before. So first off, finding inertia matrix, we didn't do it before with our completed satellite, and we used the CAD model to estimate our inertia matrix. But the problem with that is that its uncertainty is very high. So when we try to run our attitude determination and control, apparently at higher angular velocities it started failing. So we had to think of another way how to estimate our inertia matrix, and that was done using simulations and matching the simulations with the behavior in orbit. So timing of control that I have already talked about, that is using basically extrapolating extrapolating the measurements to the right control time and things like that. So coil output distortion was one of the biggest hurdles we had. That is basically, I will talk about the magnetic problems in the next slide, and I will just mention it here that the residual magnetic moment is also what I will talk about now. Magnetic influence. So basically, we have satellite has residual magnetic moment that is of the same order that we can produce with coils. That means it's almost as big or even bigger. We can't be 100% sure. And it is aligned along the minus x plus z in satellite axis. It's hard to imagine, but if the animation clears that up again. And it basically makes pointing impossible, and the inertial alignment turns things up very hard. So hopefully now we have an animation. Maybe. Yay. Okay, so it's very hard to understand, but basically, if you know how the Earth's magnetic lines go, they go around from the poles up and then do the full half circle and go back into the other pole. And basically, this is the rotation axis in the inertial frame, and this goes together with the magnetic field, and it follows it basically during the orbit. This means that the magnetic field creates a strong enough force that it just points our satellite according to the magnetic field, which means basically that even if we try to keep it aligned, basically our idea is to keep it aligned with the Earth axis, the satellite all the time. But because the magnetic force is disturbing it all the time, it means that we are unable to keep it in that orientation. We tried something and we have some good results with it, but it's not good enough to do the experiment under these conditions. I will show a bit more about that later. And our response to the magnetic disturbance is what we did to fix the problem and how we can spin up now very well and up to 360 degrees per second and maybe even more, because in the following days now we will try to spin it up more in about a week or so. And what we did is, first off, we changed our rotation to be around the magnetic vector, which meant that we can still spin up the satellite well around the magnetic vector, and that is what we did. So this doesn't matter for inertial alignment, it doesn't help, but in satellite body frame we can still spin it up well. So now we're spinning up around minus x plus z axis. So this is some weird axis. It's really hard to, if you have a cube, you can play around with it. It still confuses me even when I've been dealing with it. And you need a cube to understand that. It's hard to understand otherwise. And then what we also did is correct the coil output, because the coils are distorted. Their output is distorted by the same materials that create the magnetic moment. So we have ferromagnetic materials on the satellite, and those create a magnetic moment that we are unable to overcome with coils alone. And the coil output function basically corrects the coil outputs. But unfortunately, we don't have a very precise model of our satellite itself, so the coil function is created by testing it in the lab, but it's not 100% same as in the orbit. So there are some differences from that, and which also mean that our attitude control isn't as good as it could be. And one of our most unfortunate responses to this problem is that we scrapped the inertial alignment during the experiment. And this also means that we can still do the experiment. It's just harder to do and harder to measure, but it's still possible. So that wasn't a deal breaker, and we went with it. So we can show one realignment test at 50 degrees per second after all of our fixes, which you can see. Basically, the idea is that the red has to be very high. That's very easy to read graph, right? Just red has to be very high. So it's very hard to tell anything else from this graph. Basically, this is the angular velocity in inertial frame. So if the other components, the x and y component, go to 0, and there is only a component around the z-axis, then it means that it's rotating around one axis only. And so, for the main objective of this talk is to tell you what we did wrong, or what we did right, and what you should also do the same way. So, try to be even more careful with ferromagnetic materials. We knew it was a problem, everybody knew it was a problem, but it still happened because of a late-minute change in one component or battery casing, which we didn't know which material it was from, and it was actually ferromagnetic. Those things still happen, but you have to be as careful as possible, and we weren't careful enough. And one more point that we could have done is include other actuators. So we could have put reaction wheels on the satellite, and that would have helped us to hold the attitude in such a way that we could have had inertial alignment. And of course, because I mentioned the inertia measurements, it would have been possible to measure it before launch and not estimate it from a CAD model. And because the attitude control algorithms at high spin rates are become very easily disturbed, then inertia is very important. Lesson 2 is be able to update software in Nordic. And as you can see, this is the only place where I use punctuation and it has 3 exclamation marks. So basically, we didn't have the possibility for attitude control or attitude determination when we launched. And the problems that the students make, they don't know before. They need the experience to estimate this problem before. And I'm totally sure that even if we had some more expertise, that we still need this being able to update the software. And the people who don't use this possibility are just crazy. It seems impossible to do it other ways because the problems are often unexpected and they might happen only under specific conditions. So another thing is like attitude determination doesn't actually require an accelerometer. So, but if we would have had an accelerometer, it would have been much easier to debug our coil outputs, stuff like that. So it's very useful for debugging. So it's very good to include one on your satellite. And the last one is have an identical prototype on the ground. As I mentioned, our coil function is still incorrect, and we should have had the real prototype on the ground that would have been exactly the same, and we would have had better attitude results. And that is it. So thank you. Do you have any questions?
As you see, we really invited the best friends to come over today, because otherwise we wouldn't have been so honest with you. But now you are most welcome to ask questions right now, or then in private during or after the lunch, after dinner. So,
I have a very generic question. When you say you would have used reaction wheels, this of course pushes the power, the volume, and everything.
Yeah, that is
Are you
exactly.
serious about like investing time and effort into that rather than maybe putting more effort on the things you listed? What would give the most return with this?
Yeah, that's why it's a lesson learned. Initially, we thought we wouldn't need it, and mass and power-wise, it seems smarter to use only magnetic coils. But when the satellite, when we are not actively controlling it with magnetic actuators, then the alignment starts going off, and that was the biggest problem. If we could actively run the magnetic controllers all the time, then we wouldn't need reaction wheels. But the problem is that running the magnetic torquers takes a lot of power, and we don't have enough power to basically do it for this experiment, for example. Adding reaction wheels is actually more power efficient when you want to control the satellite when you don't need to change it that much. So we just keep it in one alignment, for example.
So did I hear correctly that your magnetic moment was 0.09 at first?
Yeah.
Would like torque rods have been more efficient? Or?
We should have, like, the main thing is maybe we should have put something in the middle of the coils, basically some different material or something like that, which would have increased the coil power. But at the same time, it takes more like current, and it seemed enough for our mission, so we went with that. But apparently, we didn't predict the magnetic influence as well. So
it is actually surprising that you can spin it in the axis that you are now doing that was.
yeah.
Because it's around the magnetic, so the spin axis is the same as the magnetic field. And I mean, it's this magnetic torque around that axis should in principle be zero, as you know, because. But I mean, I guess since it works, it must depend on some on the fact that these axes are not. This axis is not exactly.
Yeah, it oscillates around
It
that
oscillates, yeah.
for a lot of the way.
And physics is slightly different here in Estonia than in Finland.
Yeah, the main thing is that the satellite naturally lacks, so it wants to go into those axes. So if we try to disturb it to spin it around the other axes, then it will it will go back to the last state and probably not spin it up at all. So, and the orbits left oscillating. But it is probably a combination of magnetic moment and inertia. So, yeah.
So the last question goes to Lithuania.
You use a P-dot controller for the tumbling?
Yeah, we use the P-dot controller for tumbling.
Any problems?
At higher spin rates, it's basically unusable. But we use the spin controller to spin down also, because it has much more improvement, many improvements over the regular simple P-dot, because P-dot is actually very simple. You just take the derivative of the magnetic field, basically.
So it was unusable because of the same problem?
Not exactly. It's more that the simplicity of it, if you example a sinusoid, how the magnetic field acts, then basically the derivative isn't good enough if it changes a lot during if the sinusoid changes a lot, basically, because it goes over it like in one second, because it's one revolution. So even small time differences and everything like that really add up a lot.
What do you mean is the discrete implementation is not fast enough for it to work as intended?
Yeah, basically. But yeah, all the timing differences are also a big problem, because the timing isn't as exact, or sensor measurement times and stuff like that become hard.
Okay, so thank you very much, Henrik. And now the current plan is such that first we go downstairs and eat, and then in a half an hour we have planned excursions, and we will be divided into two. One group will go and take a look at our robotic telescope and our large optical telescope, and then we'll come back. The second group will go to the electronics lab, space technology testing lab, EMC lab, ground stations, mission control center, and then we switch. So you will see everything. And if you have seen it all, some of my students were here just last week, then you are most welcome to just sit, relax, and enjoy conversation with other people. So excursions are not mandatory, but if you want to see it, then at 7 o'clock we start downstairs at the cafeteria. And we leave at 9 o'clock.